Ladies and gentlemen, please extend a very warm welcome to our keynote speaker this morning, Dr. Omkaram Nalamasu.
Good morning. Good morning. So my apologies up front. I have a bit of a hoarse throat. One of my colleagues suggested that I should sing a song to clear up my throat, but I would be very kind and would not do that. Instead, what I like to do is talk about semiconductor manufacturing. The way we define this is basically materials engineering. If you're looking at semiconductor manufacturing, it is really about atomic control of matter with precision and essentially having control on surfaces and interfaces, and certainly driving the semiconductor industry in the past, and it's going to drive in the future. But more importantly, we believe that materials engineering is a fundamental capability in advancing multiple inflections that are going to shape the future of the world. So I'll certainly talk about electronics, I'll certainly talk about entrepreneurship, and I'll talk about the impact of this industry on the economy. So for those of you who may not know Applied Materials as a company, what Applied Materials today, I'll give you a brief introduction. First of all, virtually every computer chip and every display and every solar panel that's made in the world uses Applied Materials technology in one way. And we also believe that this is foundational technology for driving other inflections as we look into the future. So today we are roughly about $15 billion in revenue, and we spend close to $2 billion in R&D. This is a intellectual property intensive industries. We have about 12,000 patents and another 12,000 in works, and roughly about 20,000 employees globally. These are the full-time headcount. In addition to that, we have contractors, and we are headquartered in Silicon Valley, and this year is our 50th anniversary. And this year is also very special for us because this is the 15th year for Applied Materials in India. We started with about 2 people 15 years ago, and we have now 2,500 employees in India, and virtually providing engineering expertise and engineering knowledge and engineering contributions to every product that we make in Applied Materials today. So our footprint in India, Bangalore is our gravity. Majority of our R&D is in Bangalore, although we also have people across India. We have 40 people working in IIT Bombay in collaboration with the students, faculty, postdocs every day. I'll say a little bit more about that. And we also have a presence in Delhi, and we also have a few hundred people in Chennai, specifically working on factory automation and data sciences. So I want to define materials engineering before I talk about what it has done for the world and how it is a solution for enabling global inflections. The way we define materials engineering is basically creating, modifying, removing, and interrogating. Interrogating meaning inspection or metrology. Materials at an atomic level on an industrial scale. So this is fundamental control on matter with atomic precision, but on an industrial scale. So you have driven the Moore's law in the past and driving Moore's law forward, but bringing similar disciplines, similar best known methods in enabling other industries. I'll say more about that. But how does materials engineering look within the context of semiconductor industry, let's say, which is really having 20 miles of copper wiring on roughly half-inch square wafer, half-inch square chip, are removing trillion contact holes. Each one of them is less than 100 nanometer in diameter with complete precision, are detecting an ant on a city of Seattle, which is equivalent to basically finding a 10 nanometer particle on 300 millimeter wafer, which is equivalent to finding an ant in the city of Seattle, basically. So what has it done? If you were to build the iPhone in 1980s using the technology that's available then, it would have been 14 meters long and would have required 200 kilowatts of power, as against, all of us know basically it's a few inches wide, a couple of inches tall, and uses less than a watt of power. So that's basically the power of semiconductor technology and materials engineering. So the aspect that I want to focus on is how this industry has transformed from an industry that is driven by lithography to an industry that is increasingly driven by materials innovations. So if you look at the number of elements that are used in making a 45 nanometer device, you are using roughly 20 elements from the periodic table. And if you're looking at making a 10 nanometer device in not a very long time, so if you're looking at from 2000 to today, you're using roughly 50 elements of the periodic table to be able to design materials and the device layers with precise electrical, mechanical, chemical, and physical properties that you would actually need. And if we do a level deeper on how these materials innovations would look, so you're looking at here basically scaling up until, I would say, 65 nanometers, the industry is really driven by lithography scaling. And if you're looking at 45 nanometers and below, so today's 10 nanometers R&D in 7 and 5, and presumably down to 2.5 nanometer, it is increasingly driven by materials-enabled innovations. So all the way from straight engineering in the past to get the mobility, to control the RC delay with high K and low K materials, address the electromigration with cobalt, and really going from 2D devices to 3D devices, whether it is at the transistor level or on the memory architectures. And if you're actually looking at future, if you're looking at 3 nanometer or below 5 nanometer devices, you're looking at very different architectures, are using different materials, silicon germanium channel or gate-all-around architectures. So the one point here is basically, again, the industry is increasingly driven by materials innovations is the take-home point from this particular slide. So what are some of the inflections that are going to be driven by materials engineering as we look at the future? So for one, semiconductors and big data and AI would continue to be driven by materials engineering. I'll say a little bit about that. Displays and augmented reality and virtual reality are two big inflections if you're looking at the world of display. That is also going to be driven by materials engineering. And I'll say a little bit about the whole disruption that is taking place in the transportation industry and connect that to what innovation need to happen within the context of batteries and how materials innovations are a fit for that. I won't have time to talk about digital manufacturing, which is basically the 3D printing, or talk about healthcare, which is also ripe for disruption on what materials engineering can do. So I would only talk about 3 inflections. One, basically big data and AI, displays, and the third one being the electric vehicles and transportation and batteries. So let's talk about semiconductors, big data, and AI. So this is an issue in May 2017, Economist. And data to this century is what oil was to the last one, a fundamental driver of growth and change. AI-related growth will boost global GDP by almost $16 trillion by 2030. A couple of weeks ago, Sundar Pichai was giving an interview. Basically, he said AI is as big an inflection as electricity in shaping the world of tomorrow. So let's look at the 3 waves of innovation in the semiconductor industry. If you're looking at the past between 2000 to 2010, industry was primarily driven by PC and internet. So you had something like hundreds of millions of devices. And if you're looking between 2010 to 2020, This is really driven by mobility as well as social media, and that is layered on top of the PC investments that are continuously taking place. But if you look at the future, if you're looking at next 10, 20, 30 years, we are talking about tens of billions of devices in going from hundreds of millions to billions of devices to tens of billions of devices, things like IoT basically. They really need innovations in the processor architecture, whether it is CPUs or TPUs or ASIC architectures. You need lots and lots of memory. This is really a game about data, and you need cheap memory, and also you need innovations in the display technology. So these three inflections are happening simultaneously in driving the semiconductor innovation, industry innovations to be able to address the needs of this inflection. So if you look at data, there is a data deluge, and more data is generated every day. About 300 billion emails are sent today, every day, and about 100 terabytes of data are uploaded per day on Facebook. And this is a little dated information. This is about a year and a half old, 230 million tweets per day. Anybody wants to take a guess if it has gone up or gone down? It's about 500 million tweets per day in the world today because of the wonderful president we elected. But if you look at the future, I think it's going to be even more data rich. If you just look at level 4 autonomous car, that's going to be generating something like 4 terabytes of data. And if you're looking at IoT by 2020, that's going to be generating about 600 zettabytes of data. So today, there is about 2.5 zettabytes of information digitally stored. And currently you're generating something like 2.7 zettabytes of data every day. And the data is only going to increase. So certainly there is an opportunity with respect to innovations in driving the cost down of the memory and making the memory much more cheaper, robust, reliable, and universal to be able to address this particular inflection. So in 2020, there is about 600 zettabytes storage capacity, and roughly 600 zettabytes of data is going to be generated just by IoT devices alone. So future of computing, transistor scaling would presumably go down to 2 nanometers. I joined this industry in 1986, and we were predicting the end of semiconductor industry somewhere around 2 microns, and here we are talking about 2 nanometer design rules or 2.5 nanometer design rules, whether you believe IMEC or Samsung. But this is about energy efficient processors, both at cloud and at edge. The second, you need innovations in the memory in going from suburban sprawl to basically skyscrapers, and you need high capacity, better performance, better reliability, but fundamentally it's the lowest cost per gigabyte of memory, better memory basically. And the third one is computing architectures. You really can't assume that computing is only going to be von Neumann computing architectures. And there is going to be innovations in non-von Neumann kind of computing, whether it is analog devices, things like memristor, or quantum computing. So let me switch gears by talking about advanced displays, augmented reality, and virtual reality. And humans are fundamentally visual animals, right? I mean, we crave for information, and the world, is really the way we sense the world, the way we interact with the world is a great deal to do with the vision, and that's why you say a picture is worth 1,000 words, and you can see how display technology is fundamental in different verticals we interact with every day. So if you look at this particular industry, it has gone through similar innovations. So if you look at the first innovation, that's the emergence of LCD as a technology. If you went back to 1995, LCD industry was roughly $1 billion. and today it's 120 billion plus. And the reason being is that you're driving the cost of a panel, processing cost of a panel, 20% every year. So if you're looking at processing meter square of a glass panel, you're driving the cost 20% year over year. As you're driving the cost down, as you're improving the resolution, this has become basically a pervasive part of our lives. And the second thing that is happening is that if you look at today, mobility basically, in mobility, basically smartphones we're talking about, the screens are going from LCD to organic LED, and as a consequence of that, the complexity is going up, and the capex in this industry is going up from something like $7 to $8 billion between 98 to 2000 to something like $17 to $18 billion. So almost doubling of display fab equipment spending. And if you're looking at future, it's going to be about foldable displays, organic LED TVs, and light field images, basically what is called natural 3D display technology. So the fundamental drivers are scaling, going from Gen 2 all the way to Gen 11. Gen 10 is basically a 3 meters by 3 meters piece of glass, and you need to process 50 panels per an hour with atomic control. So this is really atomic processing or materials engineering on a very large scale. The second thing that happened is that the resolution is going up from 1080 to 4K. Now we are talking about 8K in the TVs, and resolution is also going up when you're looking at the screens for your smartphones. And form factor is important. If you're looking at mobility, it's all about form factor. How much information can you put with respect to memory, and how bright the screen is, and whether it is flexible or bendable and things like that. And in the future, you're looking at true displays, which are like the light field displays. So from a technology perspective, as I said, the resolution is going up. Form factor is going from fixed to curved to rollable, foldable, and the size is essentially going up. As you are going for higher resolution and as you are going to OLED displays, the backplane technology is going from amorphous silicon to metal oxide TFTs, thin film transistors, low temperature polysilicon. And industry, as I said, is going from LCD to OLED, fixed to flexible, and 2D to 3D. And a related innovation that is getting a whole lot of attention is the augmented reality and basically virtual reality. Mark Zuckerberg basically said that this is a good candidate to be the next major computing and communication platform. And Scott Adams said that when VR gets cheaper than dating, society is doomed. So whether you believe this or that, or you believe both, I think VR, AR is going to be a big industry. Projections are that this could be something like $150 billion in 2020. Majority of that being in the augmented reality, and a small fraction of that in the virtual reality. So if you look at the mobile phone industry, and if you went back to 1980s, this is Michael Douglas in the movie Wall Street, and he uses this particular phone, and this is called Dynatex, I believe. This is basically 2 pounds and 13 inches long, had no inbuilt memory, and basically was costing $4,000. That was state of the art in 1987. And if you look at today, of course, the iPhone 7 is somewhere between 100 to 200 grams, and it is more powerful than the supercomputer of 10 years ago. The reason I'm giving you this example is that similar innovations need to take place in the context of augmented reality and virtual reality. Again, Michael Douglas in movie 1994, Disclosure, and if you look at the cool augmented reality, virtual reality glasses he's wearing compared to what is reality today, So you really need to go from here to there in order to create the next $100 billion industry for AR, VR, with innovations similar to what took place in the context of smartphone. So what need to happen? There need to be innovation on multiple fronts. There need to be innovations in electronics, basically on the packaging front. There need to be innovations in the display. You certainly need to go from LCD to organic LED from a switching speed perspective of the device. They need to have a compliant form factor. The resolution has to go from something like 500 PPI to 2,000 to 3,000 PPI. So if you're looking at an augmented reality device, you need significantly more than 2,000 PPI. For a VR device, you can get away with less than 2,000 PPI. Displays going from opaque to transparent and conventional to light field displays. And presumably, batteries are integrated with the device itself. So you need solid-state batteries that have very high energy density. And optics. Again, this is an exciting area, actually. The whole engineered optics is a new area of interest. There is a lot of activity in the academia, in the startups, basically. Fundamentally, you want to get the performance of the bulk optics in the thin films, which are typically sub-100 nanometer design rules. And if you can do that, you can really see transforming this industry from something like this to non-obtrusive glasses that you can actually wear. So the next one is transportation, basically. If there is one industry that is going to be disrupted more than any other in the next 20 years, probably transportation. It is ripe for disruption, and it is getting disrupted from multiple sides. So this is a quote from Elon Musk talking about in 10 years, more than half of new vehicle production is electric in the United States. And in 20 years, there will not be a steering wheel, and it will be like having a horse. So let's talk about what are the inflections that are going to drive this industry forward. So one is basically electrification of vehicles, right? If you compare between 2018 to 21, 11 manufacturers have announced plans to introduce level 4 vehicles in the next 2 years. So we're talking about automation here. We're talking about level 4 automation here. And the next thing is basically electric vehicles. Multiple countries, something like a dozen, have announced last year that they're going to stop allowing IC engines and essentially go to electrified vehicles. India itself announced that in 2030, they want to phase out diesel and petrol cars. So Morgan Stanley, your car is arguably one of the most underutilized, polluting, time-consuming, and dangerous machines on Earth. So if you look at the car, there are about 2 billion cars. Let's assume that each one is about $15,000 in value. So you have something like $30 trillion worth of assets globally, which are used less than 4% of the time. So it's a colossal wastage of global resources. The second one is basically the fatalities on the road. About 1.3 million annual fatalities globally, and vast majority of them are because of the human error. And if you look at IC engine, it's very, very inefficient. It's only 15% efficient. 85% of the fuel never reaches the wheels. So what are the inflections? Everyone heard about shared economy, whether it is Uber in the United States or Ola in India. Autonomy, basically we're talking about driverless cars, and that has a potential to eliminate 90% of accidents. And electric motors are much more efficient. So you can go from something like 15% efficiency to 67 to 81% efficiency. So let me connect this to materials engineering innovations that need to happen to make this particular inflection a reality. So this is Jensen Huang, NVIDIA CEO. The quote is, if you add enough sensors like LiDAR and radar and high dynamic range cameras, in combination, we'll be able to surpass human perception. Okay? So if you're looking at sharing economy, autonomy, and electrification, you need sensors, memory computing, you have communication systems that are required, V2X, vehicle to vehicle, vehicle to pedestrian, vehicle to cloud kind of innovations. Displays, again, you need to have high resolution displays in your vehicle, and fundamental inventions need to happen in power electronics, whether it's silicon carbide or gallium nitride. One thing I would say is high energy density batteries are also very critical for the electrification of vehicles. I'll say a little bit more about that. So you need continuous innovations in semiconductors, you need innovations in compound semi for autonomy and electrification, and energy storage. There need to be innovations, and displays and optics. And let's drill down a little bit more into the energy storage. So fundamentally, if you're looking at a battery, costs need to come down, charging speed need to go up, safety is of paramount importance, and the energy density need to go up. And this is true whether it is electrification of vehicles, or this is also true if you're looking at drones, or for a battery that probably lasts a week rather than a day on a smartphone. So today, if you're looking at cost per kilowatt hour, is something like $200, and you really need to go down to something like $100. So the way you could do that is to increase the energy density, and there are multiple ways you could increase the energy density, but one of the most practical, cost-effective, and safe ways to do is to be able to change the anode from graphite to silicon graphite to lithium anode, and the expected production is 2020 to 2025. And also within the same time frame, 2025 and beyond, one can also have solid-state batteries which do not have any liquids that are flammable as well. The only takeaway point from here is basically batteries, I think, is ripe for inflection. If there is a Moore's law for batteries, there is doubling of the energy density in something like 7 to 8 years. There is opportunity to accelerate that, drive the cost, make the electrification of vehicles a reality with materials engineering innovations in this context. So I have a couple more minutes, and what I want to talk about is open innovation, and we have a ventures arm called Applied Ventures. I'll talk about the entrepreneurship and how we work with entrepreneurs who are taking good ideas to the market, disrupting the industries that we talked about. So I don't know how many of you know this concept of open innovation. The gentleman who introduced this concept is Professor Henry Chesbrough from UC Berkeley. And what his idea basically is that in today's world, no company, no country, no university has all the intellectual, financial, or infrastructural resources to be able to address the opportunities that are out there by themselves. So one needs to look at expansively and think of collaborating with universities, working with the startups, talking to the customers, talking to the partners. So you have a cost-effective pathway of taking a time through this innovation funnel, addressing a new market or a current market, basically. And this is a holy funnel, so ideas can come in and ideas can go out. But fundamentally, you need to think of the competencies and capabilities that are available across the globe and connect the dots in interesting ways so you have a time-effective and cost-effective commercialization. So let me talk about the first component, that is working with universities within this context. So we've been collaborating with IIT Bombay for the last 12 years. We have invested something like $15 million in IIT Bombay, and there is a building named after Applied Materials in IIT Bombay. We have roughly 40 people from our organization placed on IIT Bombay campus, working with the faculty, students every day. And And we believe that this is a global benchmark for academia-industry collaboration, especially a global company working with an Indian institution of higher learning. There are quite a few milestones and accomplishments. I'm not going to bore you with them, but this is really a comprehensive relationships where we hire students, provide some summer internships. Some of our employees are actually part-time faculty on IIT Bombay campus, and we take some of the faculty from IIT Bombay on sabbatical to applied materials. And the facility we have with them is actually used by almost 70 R&D institutes in India to do fundamental research related to electronics. The second piece I want to talk about is applied ventures. This is the venture arm of applied materials. We have about $250 million assets in different investments. We have invested in over 70 companies in the past, and at least 35 of them are still active, and we have the ability to invest up to $50 million a year. Basically, this is an evergreen fund. We invest all the way from seed through growth stage startups, and we work with other corporate VCs as well as financial VCs. And we have venture investment professionals in about 6 countries, investments in more than a dozen countries across the globe. So this is just a segmentation of our investments in semiconductors, 3D printing, energy, next generation displays, big data, artificial intelligence, life sciences, and display and adjacent markets. As you can see, these are all the verticals that I'm interested in. I was giving you kind of a peek into our thinking. So just want to talk about India, the last one. The honorable minister talked about this. If you look at India, we have 2nd largest telecommunications market today, 4th largest auto industry in the world, 20% of global generics market, and implementation of LED for energy efficiency, and 20 gigawatts of solar installed in 2018. The point here is that India has proof points in technology scaling. When policy and industry works together, you could do wonderful things. And we also heard in the morning about a vibrant ESDM industry in India and how it is growing by leaps and bounds in semiconductor design, our consumption of TVs, our telecom equipment. Obviously, what is missing here is manufacturing of TVs or manufacturing of a semiconductor fab in India. So that's certainly an opportunity. So my message is basically, hopefully I convinced you that materials engineering innovations are fundamental to driving semi and display forward. But more importantly, hopefully I convinced you that this is a fundamental capability that can address multiple global inflections that are going to shape tomorrow's world. We like to believe that we have fundamental capabilities and work with our customers passionately in driving these innovations. Last but not least, I think there is still an opportunity to have materials engineering-based industries to have this Make in India reality from that perspective. So thank you for your attention.
I'd like to request Mr. Sompal Chowdhury, partner, Bharat Innovation Fund and IASA Executive Council member, to present a small token of our appreciation to Dr. Omkaram.